Hello, my name is Anthony Sent, and this is Physics Lab 5. So in this presentation, I'm going to be giving an introduction to the experiment, go a little bit more in depth on the procedure and results, and then I'm going to be talking about a computational model that I made about the experiment, and then discuss and analyze some hypotheticals and some of the reasons why we saw what we saw with these experiment and models. So the purpose of this lab was to test how long it takes to get a magnet to fall to the ground in free fall versus through a tube of aluminum foil, and then compare those times to a computational model. In the results, I found that it took about 0.215 seconds to fall in free fall. Through the aluminum foil, it took about 1.09 seconds, and the computational model said that it should take 1.122 seconds. So some important physics concepts are going to be Faraday's law, Lenz's law, and Newton's second law. These are really only going to apply to that computational model, but they are at work in the real world when we're doing the experiment. These formulas are straight from the formula sheet from the internet, and they will be applied in the computational model. So going into the experiment, the free fall trial was a magnet just dropped from about 30 centimeters and timed. The aluminum foil model, or side of things, was the magnet dropped through a tube of aluminum foil. Again, it was about 30 centimeters long, and then the time for it to fall to the ground was measured and averaged over those three trials. And the reason that the aluminum foil trials took longer to fall was going to be due to Lenz's law, which I will discuss a little bit later. Initial conditions here, the tube was 0.3 meters or 30 centimeters long, the magnet was 0.023 kilograms, and the magnitude of the magnetic dipole was 2.97 coulombs, and that is from Lab 3. So here are my results from each of those three trials averaged out to get that 0.216 and 1.09 seconds, respectively. So here in the computational model, it is broken up into 8 parts. Here are the first 3. The first part is talking about the initial conditions. So the width and inner radius sections are just going to be the thickness of the aluminum around the in the aluminum foil tube, and then mass and magnetic dipole, which again, Lab 3. That second section there is calculating the dipole magnetic field, and then the third section is calculating the flux according to Faraday's law. Step 4 is creating a ring, and there are 2 rings modeled in this experiment that I will talk about in 2 slides. Steps 5 and 6 are dealing with some forces, so the force on the ring and the force on the magnet. Step 7 is getting that net force. So it's taking in the gravitational force using the mass and gravity, and then that magnetic force calculated in the last step. So step 8 is just putting the model together and updating the velocity and position of the bar using Newton's second law. So here on the left-hand side, you see that red ring. There's also a blue ring, which they both fell when this model was running, but I couldn't get it to show here. The red ring represents a clockwise current, while the blue ring represents a counterclockwise current. The computational model said that there would be a fall time of 1.122 seconds. So these peaks and dips there are those currents changing. So the computational model said that 1.122 compared to that 1.09, and the reason that these are different is because of the net forces on them are different. There's going to be maybe some air resistance in the real world. Maybe that cardboard tube that the aluminum foil is wrapped around has something to say about it. And then the reason that they are different from the free-falling example is, again, just Lenz's law. So going into a little bit of discussion about some what-ifs. We have the resistivity. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, if we have no resistivity from the metal, that means that the current, just taking this this formula straight from Lenz's law, that R is going to go to 0. So if that R goes to 0, that means that I is going to go to infinity. So the current will become very, very large. Now, practically, this is just because if there's no resistance, like kind of holding the thing up, you can think about it, then it's just gonna go down. Like it's not gonna be held up. So what if the holes or slots were cut into the tube? How would this affect the ring currents in my model? So the current wouldn't close properly. Lenz's law primarily works on closed loops. So the Lenz's law would have less of an effect, and that would result in a faster fall through the tube. So that's all I have for this video. Thank you for watching, and have a good one.